UVC radiation is a well-established technology for germicidal applications, and its potential in combating the spread of COVID-19 has stimulated much research activity and many product developments. UV photons in the 200 to 280 nanometer region are absorbed by DNA and RNA, causing changes to the microorganisms that render them unable to replicate. Peak DNA absorption typically occurs around 265 nanometers, so there's opportunity for LED technologies to offer greater germicidal efficiency compared to the conventional low-pressure mercury lamps that emit at 254 nanometers. Knowledge of DNA, RNA spectral absorbance, as well as the LED's absolute spectral power distribution, is needed to optimize germicidal efficacy. Far UVC sources, such as Excimer lamps emitting at 220 nanometers, are also of particular interest for germicidal use, and here too there's a good scope for UV LED developments. A significant limitation in the widespread use of UVC radiation is that it presents a photobiological hazard to our skin and eyes. Various safety standards exist, with IEC 62471 being a widely applied product standard. In general, standards refer to the long-established ICNIRP weighting function for actinic UV, and a daily limit of 30 joules per square meter is often referred to. Note the very steep slope on this graph. The weighting function varies by around 4 orders of magnitude in little more than the bandwidth of a typical UV LED. This means that high dynamic range spectral measurements are essential for photobiological safety measurements. This year, the ACGIH have published changes to the actinic UV hazard function in the far UVC region. This results from research demonstrating that whilst far UVC is strongly absorbed by biological materials, it doesn't penetrate the outer layers of dead human skin, but it does penetrate viruses and bacteria. This change creates opportunity for far UVC germicidal sources to be permanently operating in the presence of people. So high dynamic range UV spectral measurements are required to characterize devices with respect to their germicidal efficacy and their photobiological safety. Double monochromator based systems are considered to be the reference standard for such UV measurements, but these are large, slow scanning laboratory instruments and often can't be used conveniently. Array-based spectrometers offer many advantages, including speed, size, and ease of use, and are therefore most widely used. However, it's essential that array-based UV spectroradiometers demonstrate measurement results comparable to double monochromator systems. In particular, this refers to their internal stray light rejection. Another very important consideration, and one that's perhaps less immediately obvious, is the effect of fluorescence in the UVC measurement equipment. Excellent stray light rejection is a prerequisite if fluorescence effects are to be investigated. When performing spectroradiometric measurements in the UV region, internal stray light is generally the fundamental limiting factor of measurement capability, and huge errors can result as shown here. There are various causes of stray light within a spectrometer, including multiple orders of diffraction, scattering from optical surfaces, zero-order reflections, and so on. All these contribute to stray light being seen by the detector. A number of techniques can be employed to reduce internal stray light. Good optical design with optimized components are an important starting point. And long pass and band pass filters are particularly useful for reducing stray light effects resulting from out of range wavelengths. The tunable laser can be used to characterize a spectrometer at any in-range wavelength, which enables a stray light correction matrix to be applied to subsequent measurements. Careful implementation of these combined stray light correction techniques does make possible double monochromator-like performance, as shown here by two particularly demanding measurements. UV solar irradiance and photobiological safety of xenon lamps both require excellent stray light rejection. Measuring the radiant power from a UV LED is most conveniently achieved using an integrating sphere. UV visible integrating spheres are either coated with barium sulfate or synthetic ptfe material. For UV measurements, ptfe-based spheres are normally selected due to their higher reflectance in the UV range. Note that this higher reflectivity requires some significant depth of material, typically several millimeters thickness, whereas with barium sulfate the resulting diffuse reflectance is largely a surface effect. Another important quality is the extent to which the materials fluoresce. This plot shows measurements of two same-size spheres, one ptfe and one barium sulfate, when illuminated with a single wavelength at 230 nanometers from a tunable laser. The spectroradiometer used had a stray light level of less than 10 to the minus 5, so all the signal shown in the 280 to 400 nanometer region is caused by fluorescence in the spheres. The measurement of these raw off-the-shelf spheres shows significantly more fluorescence in the ptfe sphere. The level of fluorescence shown in the previous slide rises from excitation with a single wavelength. When measuring a UV LED with some finite bandwidth, the fluorescence effect will be much greater. This plot for a simulated 230 nanometer LED shows the fluorescence components to be in the region of 20% of the real peak value. This would result in a huge measurement uncertainty arising from the absorption of the LED's emission and the fluorescence emitted at longer wavelengths. The dominant cause of the fluorescence lies in contaminants such as hydrocarbons and other organic material which form on or penetrate the surface of the sphere coating. There's no significant fluorescence from the intrinsic ptfe or barium sulfate. Various conditioning treatments are known to be effective in reducing the fluorescence. In essence, they involve a combination of heat treatments and intense UV irradiation. We've been investigating the various conditioning treatments on both ptfe and barium sulfate spheres for an extended period. The important finding is that the fluorescence can be reduced significantly more in barium sulfate coated spheres than in ptfe spheres. In our example 230 nanometer LED, the measurement uncertainty resulting from the residual fluorescence equates to approximately 0.1% in the barium sulfate sphere, but around 1% in the ptfe spheres. So despite the higher throughput of ptfe spheres, barium sulfate can be a better choice for UVC type LEDs. The greater residual fluorescence in ptfe spheres largely results from the contaminant fluorophores being relatively deep within the ptfe material and are therefore more difficult to remove. They also exhibit a multiplying effect due to the volume scattering of the UV radiation within the material. Another consideration is the fact that fluorescence will return when an integrating sphere is used and stored in normal laboratory conditions. The rate of return of fluorescence is affected by the prevailing ambient measurement and storage conditions. However, in all cases, the fluorescence does return over a period of time. Therefore, it's necessary to have some long-term means of monitoring and removing the fluorescence. So, some key points. Fluorescence is a potentially significant source of measurement uncertainty when measuring UVC LEDs. Fluorescence can be caused by calibration sources, notably deuterium lamps. Fluorescence is produced by contaminants in the sphere and not the sphere material itself. Fluorescence can be significantly reduced by conditioning treatments such as high-intensity UV irradiation and can be reduced to a greater extent in barium sulfate spheres than in ptfe spheres. Fluorescence will return under normal laboratory conditions, so ongoing conditioning is necessary for long-term use. Whilst fluorescence effects are strongest with far UV excitation wavelengths, it does occur to some extent across the entire UVC range. For example, fluorescence resulting from 254 nanometers is shown here. And don't forget that stray light rejection is not only important for photobiological safety measurements, it's also essential for identifying fluorescence effects. Fluorescence is an important consideration when a deuterium lamp is used for calibration purposes. Even if you're measuring a UVA LED, fluorescence will be generated by the calibration lamp, even if not by the UV LED under test. So a best practice UV spectroradiometer system for measuring the radiant flux of UVC LEDs would incorporate a stray light corrected UV optimized spectrometer. The integrating sphere should include an auxiliary lamp for self-absorption correction, and the sphere, whether barium sulfate or ptfe, should be preconditioned to minimize fluorescence effects. A barium sulfate sphere offers the possibility of lowest fluorescence. A 2-pi geometry calibration lamp should be included with traceable calibration. And finally, a conditioning lamp can ensure long-term fluorescence-free measurements. Thank you for your attention.